Ice skating, ice fishing, building an igloo, drinking an ice-cold beverage. We humans sure love our ice. While we might think of ice as just frozen water, there's more to this slippery substance than meets the eye. You might be wondering, why doesn't ice sink? The answer has to do with the molecular structure of H2O and some serious physics. When water freezes, its molecules form a crystalline structure.
Ow.
Let's take a closer look at what makes ice so special. Ice is less dense than liquid water, which is why it floats instead of sinking. The difference in density between ice and water is actually pretty significant. A liter of liquid water weighs about 1 kilogram, but a liter of ice only weighs about 0.9 kilograms. This means that ice is about 9% less dense than water. But why does this happen? Why is ice less dense than water? In order to understand why ice floats, we first have to learn a little bit about its molecular structure. Water molecules are made of 2 hydrogen atoms and 1 oxygen atom, hence the chemical formula H2O. But the way these atoms are arranged and how they interact with each other is more important than their types. The electrons in the bonds between hydrogen and oxygen tend to migrate or shift from one molecule to another. When the electrons settle down on a different water molecule, that molecule becomes slightly negatively charged, and the original molecule becomes slightly positively charged. Remember, opposite charges attract, and like charges repel. So the positively charged end of one water molecule is attracted to the negatively charged end of a neighboring molecule. These attractive forces are called hydrogen bonds because the positively charged hydrogen ends are attracted to the negatively charged oxygen ends. And don't get confused by the name. Hydrogen bonds are not really bonds. They're more like very weak attractions. Hydrogen bonding also occurs in liquid water, but the molecules move around so much that the bonds break and reform all the time. However, when water freezes, the molecules slow down, and the hydrogen bonds become more stable. In fact, once water reaches its freezing point, the hydrogen bonds between molecules become so stable that they stay fixed in place and create a lattice structure. This structure resembles a honeycomb more than a puddle. The hexagonal shape of ice's molecular structure creates empty spaces between the molecules. As a result, ice is less dense than water. It may seem counterintuitive, but when water freezes into ice, it expands in volume by about 9%. This means that the same amount of water molecules take up more space when they're frozen. That's because those empty spaces we mentioned before come into play. The molecules can't move around and fill up these gaps like they can in liquid water. If you think about a crowded room full of people who can move around freely, it's a good representation of liquid water. But if the people in the room are arranged in a regular pattern and couldn't move around anymore, it's like a honeycomb. This is similar to how ice is structured. The hydrogen bonds holding the molecules together in ice make them rigid. The molecules can't move around to fill in the empty spaces. It's worth noting that water is almost unique in this regard, else liquids become more dense as they freeze. However, water is an exception due to the unusual nature of its molecular structure and hydrogen bonding. If water were to behave like most other liquids and become denser as it froze, ice would sink rather than float. And here's why that's a good thing. If ice sank, it would eventually reach the bottom of lakes and oceans, where it would continue to freeze and become part of a solid mass of ice. This would make it difficult for fish and other aquatic animals to swim around. All living things need oxygen, so this would be bad news for us humans and many other organisms. Additionally, ice forming at the bottom of lakes and oceans would insulate the water below, preventing it from freezing all the way through. This would allow aquatic life to survive in freezing temperatures. Have you ever seen a pond or lake that's frozen over, but has a small hole in the middle? That hole is called an ice hole, and it's formed because ice can't conduct heat very well. So the water underneath the ice stays liquid and can support aquatic life. Let us go back to that crowded room analogy to better understand why ice is less dense than water. Imagine the people in the room are holding hands and standing in a hexagonal pattern. The room is still crowded, but there are gaps between the groups of people. If you squeeze the room or apply pressure, the people will move closer together and the gaps will disappear. Now, the room is even more crowded. In effect, applying pressure compresses ice, forcing the molecules to move closer together and eliminating the open spaces. In other words, ice is most dense at 0 degrees Celsius. which means that ice is densest when it's under the most pressure. That's why you often see ice at the bottom of lakes and oceans. As more ice forms on top of it, the pressure increases. This causes the ice at the bottom to become denser, which helps it to sink and stay at the bottom. Buoyancy is a key concept in understanding why ice floats. Simply put, buoyancy is the upward force exerted on an object submerged in a fluid like water. According to Archimedes' principle, the buoyant force acting on an object is equal to the weight of the fluid it displaces. In the case of ice floating in water, the buoyant force is equal to the weight of the water displaced by the ice. For an object to float, the buoyant force must be greater than or equal to the object's weight. If the object's weight is greater than the buoyant force, the object will sink. Therefore, for ice to float, it must be less dense than water. As we already know, this is true because of the unique molecular structure of ice and the resulting open spaces between the molecules. There are several factors that affect the density of ice, including temperature, pressure, and impurities. For example, impurities such as salt and sugar can lower the freezing point of water, resulting in a less dense form of ice. This type of ice is often referred to as fresh water ice to distinguish it from regular ice that forms on bodies of salt water like oceans. Freshwater ice is about 10% less dense than seawater, which contributes to its ability to float. Another factor affecting the density of ice is pressure. As mentioned earlier, increasing pressure on ice causes the molecules to move closer together and eliminates the open spaces responsible for its low density. At standard atmospheric pressure, ice is less dense than water. However, as pressure increases, the density of ice also increases until it eventually becomes denser than water. This is why ice at the bottom of a lake, where it's subjected to greater pressure, can sink. Well, let's talk about the shape of ice. An irregularly shaped piece of ice may sink, because its heavier portion can sink while the lighter portion remains above the surface. On the other hand, ice, with a more regular shape like a cube, is more likely to float because it has a greater surface area in contact with the air, allowing more of it to float. So why does ice float? Because of the unique molecular structure of water and the resulting open spaces between molecules, ice is less dense than water. This allows ice to float in water, which has several important implications for aquatic life. If ice did not float, it would sink to the bottom of lakes and oceans, making it difficult for fish and other aquatic animals to swim and preventing oxygen from dissolving into the water. Additionally, ice forms at the bottom of lakes and oceans. It acts as an insulator, preventing the water below from freezing and allowing aquatic life to survive in freezing temperatures. I hope you enjoyed learning about ice and its unique properties. Thank you for watching. Remember to subscribe for more fun science videos.